All right, hello, welcome to this week's Math 2413 weekly review. This week we're going to be covering section 5.1, which is areas and distances, 5.2, which is definite integrals, and 5.3, which is the fundamental theorem of calculus. Just a disclaimer before we start. 5.1 and 5.2 are pretty dense sections, so if we do not have a lot of time to do examples, or if maybe like a small thing has to get cut out, I'm sorry, but because of limited time constraints, we're going to have to kind of just push forward and see what we can get done within the time. All right, now with that being said, let's go ahead and get started with 5.1, which is going to be areas and distances. All right, so let's say we want to find the area of any normal polygon. We know that like a square and rectangle, like a rectangle is going to be, the area is going to be length times width. If we want to find like a normal, like a regular polygon, if we go all the way back to like high school geometry, like let's say we have like any polygon, like hexagon, pentagon, whatever, we have that formula A equals 1/2 apothem times perimeter. These are pretty easy for regular polygons. Ones that where everything is just nice pretty angles and like stuff like pentagon, hexagon, your side lengths are the same, things like that. Now when we get to irregular polygons, things get a little different. Let's say we have something that's kind of shaped a little like this. We can't just pull out a formula from our geometry textbook to tell us how to find this area. But what we can do is we can go ahead and we can kind of break this up into little pieces. Like we can make a triangle here, make another triangle here, and then kind of break this off into a triangle and a rectangle. And what we can do is we can kind of just find the areas for each piece, for each little piece, and then add them all up, and that will get us the full area. What happens if we have something that's curved? Let's say we have something that kind of looks like this, or a common example is going to be on a graph. Let's say we're trying to find the area of a curve that looks something like this. We can't really just kind of break this up and be like, oh, there's a triangle here, there's a rectangle here, or anything like that. That's not going to get us an approximate area just because this is curved, we can't really break this up into polygons. But what we can do is we can actually approximate. So let's say what we can do is we can actually, let's say we can break this up into little rectangles. So we can see these rectangles are all the same width. What we can do is we can actually go ahead and use the area of each rectangle. So A1 plus A2 plus A3, and so on and so forth. And we can use that to approximate the area under that curve. Now we can't say that that is the area, because if we go ahead and look at this, we may have some pieces missing and some excess pieces. It depends on where we measure from. So, for example, if we have, we can go ahead and take this from our left endpoint. Our left endpoints, find those rectangles and find each of those rectangles, or we can go ahead and use our right endpoints. We can see that those aren't always the same height, and depending on where we're at, there may be some excess or some pieces missing when we have the whenever we take that. So, but we can say that that's going to be an approximation, though. And yeah, and we can go ahead and actually split this up into two separate types, I guess. We can have our left endpoints, and that's what it sounds like. It's we're going to measure out from your left endpoint. Your right endpoint, you're going to measure from your right endpoint. And this is going to be in order to find like your height of your rectangle, because right here, you can say like you know what this x is going to be, especially if they're all the same. You can figure out where that x is, but your height can change. So like you have your right endpoint, which gives you one height. And in this case, your left endpoint gives you another height. So it's important to kind of note which one you're going to use to approximate. So what we can do is we can actually, like I said, we can go ahead and we can break this up and add the sum of each of these rectangles together. So let's kind of see how this works in an example. In this one, we're going to have the graph. We're going to go ahead and let's draw our graph. And we're going to have our graph is going to be the function y equals the square root of x. And let's say we want to find the area under our curve, y equals square root of x, from the area from the interval 0 to 4. And we're going to go ahead and we're going to use 4 rectangles to approximate. So let's see, right here we've got our 0, we've got our 4 right here. All right, so they want us to go ahead and use 4 rectangles to mark this off. So what we can do is let's go ahead and see how we can split this 4 ways. So if we're going from 0 to 4, we can have one rectangle from 0 to 1, another from 1 to 2, another from 2 to 3, and another from 3 to 4. That's going to give us 4 rectangles. So what we can do is we can go ahead and mark off on our graph where this is going to be at. We're just going to pretend that these are all the same length because I can't draw. So the thing is, like we said earlier, we can get 2 different areas. We can get our left and we can get our right. Let's go ahead and look at both and go ahead and solve for both, just to kind of see if that gives us an idea of what we're looking at. So if we look down here, we can see that right here, these are all this x is all going to be the same length. So these are all going to be 1, or give us a width of 1. Our height, so we know that our w is always going to be 1. Our height of our rectangle is going to be, once again, that's going to kind of be determined by which side we want to use. So in this one, let's go ahead and we can go ahead and start off with our right. So we're going to go find that point on f of x, and it's going to be the right side of that rectangle. So from 0 to 1, onto the right side, and we measure off from there. And we keep going out like this. And then for the sake of time, I went ahead and let's go and look and see where we're at for each of these. We have at x equals 1, you get y equals 1. X equals square root of 2, that's going to be, square root of 2 is probably going to be 1.4. Square root of 3 is approximately going to be 1.7. And of course, square root of 4 is just 2. So what we can do is now that we can now have our width and our height for each of these. So what we can do, so what we're really doing is we're looking at each of these pieces. This little section, this section, and then this section. So what we can do is we can go ahead and add up each of these. So we can say our area from our right is going to be 1 times 1, because that's our first, plus 1 times 1.4, plus 1 times 0.7, plus 1 times 2. And if we go ahead and add all that up, that's going to get us 1 plus 0.4 plus 1.7 plus 2. And that is going to go ahead and give us a value of 4.1. Now let's look and see what happens when we go ahead and use our 11 point. So from here, we're measuring from our leftmost side. So we have 0 right here. Then we measure from 1 to 2. So from 0 to 1, 1 to 2, 2 to 3, and then 3 to 4. So now let's look and see what we get. We have 0 right here, and then we still keep our 1, our 1.4, and our 1.7. So what we can do right here is we can say that our area from the left is going to be 1 times 0 plus 1 times 1, 1 times 1 plus 1 times 1.4 plus 1 times 1.7. So that's going to get us 0 plus 1 plus 1.4 plus 1.7. And that is going, wait, I misadded right here. Our left endpoint is going to get us 4.1. Our right endpoint gave us 6.1. I apologize, I misread my notes. So we can see that we have these two different areas, one's bigger and one's smaller. But we also know there's also some, with our left endpoints, we can see that we are missing big chunks. Like we had this, so from right here, we didn't even have anything for this one. We had this chunk missing, and a little bit right here missing. So we can see that one's going to be it's going to be under. Whereas with our right, we can see we went over, because we can see that we had this chunk right here, this piece right here, this piece right here, and this piece right here. So we have an underestimate and an overestimate. So what we can do is we can actually set up an inequality to say that our area is going to be in between 4.1 and 6.1. So that kind of gives us a rough idea of where we're at. But let's go ahead and think about what happens if we use more rectangles. If, let's say, we want, let's go ahead and let's plug in with more than 4 rectangles. So we're going to have our same function. We're going to catch it off with several more thinner rectangles. And now let's go ahead and measure our left and right endpoints. So we can go ahead and get our left, we're getting from here, 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 and then so on and so forth. Now we can also look at our right and see what we have. In this one, if we actually go ahead and pay attention, we can actually see that whereas we had some really, really big gaps in that first one, for each of these are actually getting a little smaller. So of course that first one's going to be a little iffy, but after that, we're not really, like our little pieces that we're missing are actually getting a lot smaller. Because we can even see up here how like they're almost just completely in line as our graph is like shallowing out. This brings up an interesting point. This brings up an interesting idea. So we're having less and less pieces missing. So that means that we're getting a better approximation of what our area is. So for example, let's say if we wanted to use, let's say if we used 8. So let's say for example, we used 8 rectangles. That inequality gave us 4.77 is in between A as less than A, which is less than 0.77. And when I calculated the actual area, that actual area is actually 16/3, which is 5.33. We can see that these areas are closer to the actual one than our initial values were. So that kind of brings us the idea that as we get more and more rectangles, so the more rectangles we have, the better approximation we get. All right. So now let's go ahead and look into some more of like the actual notation behind this. So we have, so what we can do is actually say the area A the area A of the region S, where S is kind of referring to that interval we had. So for example, in that last one we said we were looking at from 0 to 4. That lies under function f is the limit of the sum of areas of approximating rectangles. So essentially, so that's kind of going off what we said earlier. But the thing is, if we can get an infinite amount of rectangles in there, that's going to get us the actual area. So this is kind of saying, hey, let's create a limit to find the sum of those infinite rectangles. So the thing is that there's actually a couple ways we can approach this. We can approach this from our right side. We can approach this using our right side to where A is equal to our right side, which is equal to the limit as n approaches infinity of f of x1 plus f of x2 plus f of x times delta x for each of these, times delta x, f of x3 times delta x, so on and so forth to f of x sub n delta x. And what these values mean is that delta x is equal to like our quote-unquote width of our rectangle, and that is going to be, so if our region S lies on the interval from A to B, and what that's going to be, that width is going to be equal to B minus A over N. And what these x sub 1, x sub 2 is that lets us know what we're looking at. So if we say that x sub 0 is equal to our A, and we can then say that x sub 1 is equal to A plus delta x, since that's one width over. X sub 2 is equal to A plus 2 delta x. And then x sub 3 is equal to A plus 3 delta x, and so on and so forth. And then eventually it'll hit x sub n, which is equal to B. And then we plug that these x, and then once again these x sub 1, x sub 2, those are our x values that we're going to plug in to our initial function to get us our height of that rectangle. And then we can also look at our left. We can also say that our area is equal, actually these are, we take our limit of our sum as n approaches 0 for both of those. So our limit as n approaches infinity of the left side in this case equal to the limit as n approaches infinity of f of x sub 0 delta x plus f of x sub 1 delta x plus f of x sub 2 delta x, and so on and so forth, until we hit plus f of x to the n minus 1 delta x. And it's also important to note, so in that last example, we saw that in that one, our right value is always bigger than our left, but that's not always necessarily the case, because let's say we have a function that looks something like this. And we split it off into a few rectangles. And then let's go ahead and look at our right. In some cases, we can see that our right is going to be over, and in some cases, it's going to be under. And then the same thing for our left. In some cases, our left is going to be under, and in some cases, it's going to be over. It just depends on whether or not you're increasing or decreasing on that interval. And this also brings us to another interesting thing. This left and right. We can also use any point we can use any x sub I starred to find the value of f, or to find our height as long as x sub I starred falls within the interval x sub I minus 1 to x sub I. And then we can say that x1 starred, x2 starred, x3 starred, and so on and so forth are called sample points. And then we can go ahead and just to kind of give you an idea of what we're thinking of, let's say we have, that's what this is saying, is that we can have any interval from xi minus 1 to xi, and then x starred can fall anywhere on here, just as long it just can't go past, it just can't fall outside of the interval, but it can stay anywhere within this interval. And there's actually and we can also go ahead and modify our original formulas to kind of show us what this means. This can also say that in a formula sense that our area is equal to the limit as n approaches infinity of f starred 1 delta x plus f star 2 delta x, and so on and so forth until we hit n starred delta x. And then this can also bring us the idea of upper and lower sums. So the area will always fall between the upper and lower sums. So the upper sum that is going to be the biggest area possible. So essentially what you do is like you pick your x starred in each interval to produce the biggest height. And then we have our lower sum, and that is going to be the smallest area possible. And similarly, you pick your point, your x starred, to produce the shortest height. So like for example, if we had a graph at something like this, and we go ahead and we pick let's go ahead and set up our points. We're going to pretend these are all the same height. So our upper sum would kind of be the highest point in each area, which may or may not be right exactly on an endpoint. So from here, like we can see, it's the same point for each of these. And down here, we can get, on this interval, it's about right here. This interval is going to be right here, and then right here. Whereas, and then for our lower sum, we pick the smallest one. So we get here, 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 really for both intervals, and then all the way down here. So then we move on to the idea of sigma notation. So sigma notation allows us to condense sums with many terms. So the way you're going to write it is that you're going to have your basic sigma. You have an uppercase sigma, which looks like this, and a little kind of like an E. And then you're going to go ahead and you're going to have, you can say that you're going to have in I equals M, and in this case, M is going to be your starting value. In this case, we're usually going to use 0. And like so, yeah, for area, wait, 1, I misspoke. And then you're going to have that go up to some n value, and that is going to be your stopping place. And then of course you're going to have some function to plug it into. That's going to be with respect to some I. So essentially what this is saying is that we can go ahead and say that this is equal to, we can say that this equals f of m plus f of m plus 1 plus f of m plus 2, and then so on and so forth until we get f of n minus 1 plus f of n. And then that is when we stop. Like for example, if we had I equals 1 to n equals 3, it would be f of 1 plus f of 2 plus f of 3. All right, it's already 4:35, so I will kind of skip going over like distance problems and stuff, but just in general, if you're given a velocity curve, distance is going to be the area under the velocity curve. Yeah, we don't really have time to get into that because we still have 2 more sections to go. So then, definite integrals. So first of all, let's go ahead and define, so like we already said, is that, so like we just established, we can find the area under a curve by setting it equal to the limit as n approaches infinity of, and we can go ahead and combine that big thing to our sigma notation to where our n is going to infinity, or so an infinite number of rectangles, starting with our first rectangle of f of x sub I starred delta x. So that would be, so essentially what that's saying is that we get f of x of x1 starred times delta x plus f of x2 starred delta x, and so on and so forth, all the way to infinity. But now let's go ahead and move on to what, so let's go and see how this relates to definite integrals. So we can say if f is defined on a to b and we divide a to b on n subunits such that delta x is equal to b minus a over n, and we let x0 equal a, x1 equal a plus delta x, and so on and so forth, as we talked about earlier. And then x sub n equals b. Oh wait, yeah, these aren't stars. We let those be the endpoints for our n subintervals. And we let x1 starred, x2 starred, and so on and so forth to xn starred the sample points. Then we can, well, then the definition of a definite integral of a function f from a to b is, oh Lord, we are running out of room. This little squiggly line from a to b of f of x dx equals the limit as n approaches infinity of that initial area that we talked about earlier. And that is just provided that the limit exists and is the same for all possible sample points. So now let's go ahead and talk about this integral real quick. So on here we have this little, let's go ahead and talk about our interval notation. So what we do is we can have this from A to B of f of x dx. All right, so what we do is this, that little line right there is called the integral sign. Then our little function is also can be referred to as the integrand. And then we have our limits. So we have our lower limit is a, and then we have our upper limit, which is b, and then those come together to be our limits of integration. So then let's go ahead and move on to Reinman sum. Reinman sums are pretty related to integrals. So what we can do is really, you know that, so essentially, the Reinman sum is really just that formula that we have been tossing about this whole time. The Reinman sum is equal to the summation from I goes from 1 to n of f of xi starred to x. Now, this one is actually not a limit because this can actually is just like an actual sum. The other one that had the limit, like this, we can actually go ahead and calculate each individual point. That other one was a limit to kind of get us the area. The Reinman sum is just going to be kind of an approximation. All right, let me see, because we are already at 4:43. So what we can do is we can actually go ahead. We'll go around how to solve these in a minute. But yeah, just need to know that's going to be an approximation for our area and therefore an approximation for our integral. So what we can do now is say we have another theorem that we need to talk about. So we have a theorem that states if f is continuous on A to B, or if f has a finite number of jump continuities, or jump discontinuities, then f is integral, we can integrate f, it's integrable on A to B, therefore the integral from A of f of x dx exists. All right, and what we can do is actually kind of interesting with integrals. We can actually go ahead and translate summations and integrals back and forth towards each other. Just based on that theorem, just based on our definition of integrals, we can go ahead and translate in between each other. So let's do a really quick example. So in this example, we want to translate the limit as n approaches infinity of the summation from I equals 1 to n of 7 x sub I cubed plus sine of 3x sub I plus e to the negative x sub I all times delta x on the interval 1 to 3. So what we can do is we can actually translate this into an integral. To integral. So what we can do is, first of all, we have this delta x right here. So what we can do is we can actually kind of just pull that out, and we can kind of treat that and just use that as our quote-unquote dx. Then, of course, we have to create our integral sign. So we can go ahead and have our integral, and they give us our interval from 1 to 3. And then right here, in this portion, essentially we can kind of treat x sub I as x. So we just have to just replace all that to get a 7x cubed plus sine of 3x plus e to the negative x. All right, so now let's kind of go over a little bit into evaluating integrals and Riemann sums. All right, so just some key things we need to keep into account when evaluating integrals. So actually, when we evaluate integrals using this method, we're actually going to go ahead and once again use that limit as n approaches infinity, I equals 1 to n of f of xi delta x. There's some things that we need to take into account when we solve this. So we have to think about how to treat I in terms of, we need to think about how we're going to treat I and m in terms of each other. So we have this little set right here, which is going to say I equals 1 to n of I is equal to n times n plus 1 over 2. So essentially, anytime we're trying to solve and we have an I, we're going to plug that in there so we can actually solve for our limit. Then I'm not going to bother with the limit since it's going to be from I equals 1 to n for each of these. So for I squared, that's going to get us n times n plus 1 times 2n plus 1 all over 6. And then lastly, for I cubed, we are going to get n times n plus 1 over 2 squared. All right, and then we have other formulas that we need to kind of use to kind of break these up and down. So if we have All right, so if we're taking the summation, we just have just a constant term in there that's just going to be c times n. And we also have, if we have a constant times a term, then that is going to be equal. We can actually just pull that constant out in front. And then we can also, then the last thing, and also go ahead and split these up through addition and subtraction. If we have a plus or minus b, we can split that up into two different pieces. All right, so I actually do want to try to do a quick example of how to go ahead and use this. So what we can do, so what I want to do is let's go ahead and use limit. So what we're going to do is we're going to use limits to evaluate we're going to evaluate 0 to 2 of x cubed, integral of x cubed from 0 to 2. So first thing we need to do is kind of figure out, so of course we're going to have our format, which is going to be limit as n approaches infinity from I equals 1 to n of f of xi delta x. And this makes sense. And then, so yeah, so we're going to have that. Now we need to go ahead and look at what our pieces are going to be. So in this case, yeah, we're going to use right endpoints as part of the problem. I initially had a Reinman sum in there, but I don't think we're going to have time to get that part. I do want to make sure you guys know how to use this part. So what we're going to do is first we need to figure out what our delta x is going to be. So our delta x is going to be 2 minus 0 over n. So therefore, it's just going to be 2 over n. And then we have to think about what our x sub I is. So we already know that our x sub 0 is going to be 0, since that's our first point. And then our x sub 1 is going to be 2 over n. And then our x sub 2 is going to be 0 plus 2 times 2 over n, which is just going to get us 4n. 4 over n. So what we can do is we can go ahead and for our x sub I is going to be equal to 2I over n. So now it's time to go ahead and set this up. So we can go ahead and plug in all of our pieces to get us our limit. I'm going to go and switch colors actually. Our limit as n approaches infinity of the summation from I to n. It's going to be, so we're going to go ahead and we're going to plug in our x sub I. So we're going to be our 2I over n cubed times our delta x. So, and then which we established is 2n. So since we're taking our summation with respect to I, because I is what's changing the term, what we can do is we can go ahead and just pull out this 2 over n out front. So we can go ahead and get the limit as n approaches infinity of 2 over n times the summation of 2i over n cubed from 1 to n. All right, so this summation is going to get us equal to 8i cubed over n cubed. What we can do is we can actually go ahead and also pull out this 8 over n cubed since we're not using that anymore. Or at least not for right now. So what we can do is we can now rewrite this as saying we have a limit as n approaches infinity of, we now have 16 over n to the 4th times the summation of I cubed. All right, and then if we go ahead and go back to those formulas earlier to get us a value of how to get this in terms of n, we already said the summation of I cubed from 1 to infinity is going to be n times n plus 1 over 2 squared. So what we can do is we can go ahead and now take our limit as n approaches infinity of 16 over n to the 4th times, if we go ahead and distribute that square right now, we can get n squared times n plus 1 squared over 2. All right, let's go ahead and see if there's anything we can cancel out. We can go ahead and let's go ahead and cancel out this n squared to give us an n squared down here. And we get an 8 up here. Wait, actually that is going to be, that's a 4 down here, which will give us a 4 up here. Yeah, we missed. So now if we go ahead and we can go ahead and expand out this piece right here to get us, so if we get, so we're going to have 4 times n plus 1 squared in the numerator over n squared in the denominator. So if we expand that numerator out, we get 4n squared plus 8n plus 4 all over n squared. If we break this up, we get 4 plus 8 over n plus 4 over n squared. And of course, we take the limit as n approaches infinity, which will get us 4 plus 0 plus 0. So therefore, our final area is 4. All right. So let's see. Let's go ahead. So I'm not going to have time to get really into midpoint rule, but essentially that's essentially going to give you, that's essentially going to give you a Riemann sum. Instead of using your left and right endpoints, you're using the midpoint for each interval. So now let's go ahead and just move on to integral properties. So integral properties, there are a lot of different aspects of integral properties. First thing we have to do is we can actually think of integrals as not being really a net area. What I mean by that is that we can say that we have our integral. We know that's equal to some area, but really that is going to be sum a2 minus a1. And essentially what that means is that We have, sometimes if we have a function, we can treat that goes both above and below an axis. And essentially, this little section that's up here is going to be A2. This section down here is going to be A1. See what that means is that we have a positive area and a negative area. So really it's saying that it's like, you can almost kind of treat this as like an absolute value. That's essentially saying that this full area, if we say that this piece, and this piece all have an equal area, let's say these are all equal, this is equal to a, small a, and then negative small a. You're not getting 3a as your area, you're only getting just a because these would cancel out. All right, so next things to think about are just some other general properties. So if we take our integral from a to b, that is actually the same as having the negative integral from b to a. That's just switching our bounds. And also, if we take the integral, if we have a to a, like we're not moving, that's just going to get us 0. Because if you think about that, that would just get us a straight line. All right, and then we lastly have just a few little basic ones. So are just about general properties of like how to manipulate these. So we have, if we have a function that is just a constant, then that's going to be equal to c times b minus a. All right, then if we have a constant times a function, we can just pull out the constant. And then lastly, if we are adding or subtracting two functions in the as our integrands, then that we can just split that up into two different integrals. All right. So then now that brings us on. All right, and then we also have our comparison properties real quick. So one of them is saying if our function is, if we have a function that's greater than 0 on the full function or just on an integral, then the integral also has to be positive. Then we also have, if f is bigger than g, then the integral of f has to be greater than or equal to the integral of g. And then lastly, if our function lies between two constants, then that constant, the small constant times b minus a is less than or equal to the integral from a to b of f, which is less than or equal to the bigger constant times b minus a. All right. Now we can move on to fundamental theorem of calculus. Sorry if things just kind of, if I wasn't able to go over anything super in detail. If we have time, I can try to see if there's anything I can go over in more detail, but I'm not sure if we will have the time. So we have fundamental theorem of calculus. So first of all, we have to start off with the basis that we can define a function g as being the integral from 0 of g of x is equal to integral from 0 to x of f of t dt. So essentially what this is saying graphically is that g of x is really our area. So if we have from t and y, and we have our function going from 0 to x, then all of this right here, that is g of x. All right, I will go back on how to find basic area. Yeah, I'm going to just skip that. On how to find basic area, just looking at a graph. Essentially, what I was going to do is just show you how we can break it up. And if we have something that's easy, that's not curved, if we have a graph that's something like this, how we can just break that up into different curves just to find the area, which will give you g of any value. But on to fundamental theorem part 1. So fundamental theorem of calculus. Part 1. So this states that if f is continuous on a to b, g of x is equal to the integral from, right, and g of x is equal to 0 to x of f of t dt, then g prime of x is equal to f of x. Given continuity and it's differentiable on the interval. So yeah, that's actually, yeah, so what that's saying is that if g is equal to the integral of f, then if we take the derivative of g, that's equal to f. So we can kind of see what this means by doing an example problem. So in this example problem, you want to find the derivative with respect to x of integral from 0 to x of 7t to the 4th plus sine of t dt. All right, so earlier like we just said, this part right here, this integral function is equal to g of x. So, and then this piece right here is going to be our f of t. And of course, we are going from 0 to x. So using our fundamental theorem of calculus, we said that g prime of x is equal to f of x. So essentially what we do is we just plug in x into t. So we just get, so if f of t is equal to 7t to the fourth plus sine of t, f of x is equal to 7x to the fourth plus sine of t, and as we said, f of x is equal to g prime of x. So 7x to the fourth plus sine of t is our final answer. But now let's think about this if we're not going from 0 to x. Let's say we have the same function. We're taking the derivative of the same thing. Instead of from 0 to x, we're going from 0 to x squared. So we have, in this case, since we don't have x, what we can actually do is we can kind of use some substitution and chain rule. So what we can do is we can actually let u equal x squared. So we can go ahead and then say that we have d over dx from 0 to u of 7t to the fourth sine of t dt. But the thing is, we don't have an x now, we have a u. So we have to go ahead and apply our chain rule properties to actually get us to a point where we can derive. So instead of having d over dx, what we can do is we can say that we have d over du of this whole integral and just multiply that times du over dx. Now we're in a spot where we can actually play with this. So if we go ahead and derive this with respect to u, this is still using our same fundamental theorem of calculus. The difference is that instead of x, we have u. So we can go ahead and say that this is equal, this chunk right here is just going to be 7u fourth plus sine of u. But we also have to remember that we multiply times du dx. So if we go back up here, we have our u is equal to x squared. Therefore, du dx is equal to 2x. So at this point, we just plug our initial value back in to get 7 times x squared to the fourth plus sine of x squared all times 2x. So right here we get 7x to the 8th plus sine of x squared times 2x, which is equal to 14x to the 9th plus sine of x squared. And that times 2x. And that is going to be our final answer. So that was fundamental theorem of calculus part 1. Now let's move into fundamental theorem of calculus part 2. And this is the fun one. So we have fundamental theorem of calculus part 2. And this says if we have the integral from a to b of f of x dx, that is going to be equal to a large F of b minus f of a where large F is any antiderivative of small f. Or just in other words, the derivative of large f is equal to small f. So essentially what this is saying is that we can take the antiderivative to solve our integral. And this is far easier than what we just spent the previous hour doing, having to plug in Reinman sums or do really long limits. So you're going to actually carry this for pretty much the rest of your calculus career. So let's kind of go ahead and just do an example of this. So in this example, we want to find the area under the curve 4x to the 7th from 0 to 1. All right, so let's go ahead and think about our fundamental theorem of calculus part 2. That said, so on that it said that if we have our integral from a to b f of x dx, that is equal to the antiderivative of b minus the antiderivative of a. All right, so let's see what we have now. Now let's go ahead and set this up. So we have from 0 to 1 of 4x to the 7th dx is equal to our f of b minus f of a. So now we just have to figure out what our large f is. So we need to find the antiderivative of 4x to the 7th. So if we do that, we have to think about our antiderivative power rule. So we know that when we derive and take our power rule, we subtract 1 and then bring the power out front. In this case, we have to add 1 to our power. Oh, okay. That was logging and it messed up. Okay. So we get x, so we have to the 7 plus 1, which is 8. And then let's think about what we have to get a 4 out front. So if we derived this, we would get 8 times what equals 4, 1/2. And we can just double check that to make sure we get f prime of x is going to be 8 times 1/2, which is 4, x to the 8 minus 1, which is 7. Yep, that brings us back to where we need to be. So now we go ahead. We can now say that we have 1/2 1/2 x to the 8th, and we can draw the little line that shows x equals 0 to x equals 1. So now what we do is we plug each of these in and take the difference. So we're going to get 1/2 times 1 to the 8th minus 1/2 times 0, d8. And then that is going to get us 1/2 minus 0. So therefore, our final area is going to be 1/2. All right, and then I think we have time to do one more example for this. So in this one, we want to okay. In this one, we want to find the area under sine of x from 0 to pi over 2. All right, so let's go ahead and look at this. So we have to go ahead and first set up our integral. So that's going to be integral from 0 to pi over 2 of sine of x dx is equal to our antiderivative at pi over 2 minus our antiderivative at 0. All right, so now let's look at our antiderivative. So our antiderivative of sine is going to be negative cosine. So we can say that f of x is equal to negative cosine of x. And of course, if we want to double check, derivative of cosine is negative sine times a negative is just sine. All right, so now we have our negative cosine of x. And we're going to look from x equals 0 to x equals pi over 2. All right, so let's go ahead and look and see what we have here. So we have, this is going to be negative cosine of pi over 2 minus negative cosine of 0. All right, so we know cosine of pi over 2 is 0. And we have minus negative, so we can do plus. And then cosine of 0 is 1. So therefore, our final area is just going to be 1. All right, so now let's go ahead and finally conclude our fundamental theorem of calculus. So fundamental theorem of calculus is exactly what it sounds like. It sets up the basis for everything going forward. And of course, we know that it has two parts. The first part stating that if g of x equals the integral from 0 to x of f of t dt, then g prime of x is equal to f of x. And then we also have that if we have the integral from a to b of our small f of dx, that is equal to the antiderivative of f at b minus the antiderivative at a. And given that the derivative of the antiderivative is just f. So let's think about what this means. So we have one saying that if we derive a function that is an so g is defined as being an integral function. And if we derive that integral function, we just get our integral function back. And then part 2 states that we can go ahead and find an area under a curve using antiderivatives. But also antiderivatives is the key point. So let's think about what we can conclude from this. Between these two parts, we can conclude that derivatives and integrals are inverse functions. Here we go. So the fact that derivatives and integrals, by the fundamental theorem of calculus, derivatives and integrals are inverse functions. That is something that we are going to carry throughout the rest of, pretty much like I said, throughout the rest of your calculus career. These two things are definitely really, really big and will be really, really helpful to you going forward. So we only have about 5 minutes left, so I don't think I really have time to get into anything else. So I'll just go ahead and conclude the session right here. Have a great evening, everyone.